Lecture 7, Distributed Mutual Exclusion Algorithms and Non-Token Based Approach. Preface, recap of previous lecture. In previous lecture, we have discussed about the global state, that is consistent, strongly consistent and inconsistent global states, cuts in a space-time diagram and model of communications. We have also seen the snapshot algorithm that is given by Lamport, and that is called Lamport algorithm to record the global snapshot. Content of this lecture. In this lecture, we will discuss about mutual exclusion algorithm for distributed computing systems such as non-token based approach, quorum based approach and token based approach for the distributed mutual exclusion algorithms. Introduction. Mutual exclusion in a distributed system. So, concurrent accesses to the processes to a shared resource or a data is executed in a mutually exclusive manner. That is, one process at a time is allowed to execute in a critical section. And in the constraints of a distributed system where there is no shared memory, there is no physical clock and the messages are basically is having unpredictable delays, but it is a finite delay. So, in that scenario, designing this mutual exclusion, distributed mutual exclusion is basically going to be a challenging task. So, we are going to see in the introduction that only one process is allowed to execute the critical section at any given time. So, in a distributed shared memory, the existence of semaphores or shared variables and a local kernel system cannot be used to implement the mutual exclusion. Hence, we are going to discuss how the distributed mutual exclusions are going to be implemented with the message passing only. So, message passing is the sole means for implementing distributed mutual exclusion. Approaches of distributed mutual exclusion. Distributed mutual algorithms must deal with unpredictable message delays and incomplete knowledge of the system state. Three basic approaches for distributed mutual exclusion we are going to cover up in this part of the lecture. They are non-token based approach, quorum based approach and token based approach. Non-token based approach consists of two or more successive rounds of message exchanges among the sites to determine which site is allowed to enter into the critical section next. For example, we are going to cover up two algorithms. They are known as Lamport's algorithm and Ricart-Agrawala algorithm for non-token based approaches. Quorum based approach. Each site requests permission to execute the critical section from only a subset of sites, not all the sites, and that subset of site is called a quorum. So, any two quorums contains a common site. So, this common site is responsible to make sure that only one request executes the critical section at any time. For example, the algorithms like Mikawa algorithm, Agrawala algorithm, they are all quorum based algorithm which we are going to cover up. Then next is the token based approach for designing distributed algorithms. So, here unique token is also known as a privilege message is shared among the sites. A site is allowed to enter into a critical section if it possesses that particular token. So, mutual exclusion is ensured because there is only one token and that is unique. So, the token based approaches are Suzuki Kazami's broadcast algorithm, Raymond's tree based algorithms. Now, preliminaries for the system model we are going to now cover up now. So, the system consists of n different sites S1 to Sn. We assume that a single process is running on each site. So, the process at site I is denoted by Pi. So, either we can so instead of saying sites, we will be now calling it as a process running on that particular site. So, site can be in one of the following three states: requesting for a critical section, executing the critical section, or neither executing nor requesting for the critical section, they are idle state. So, in requesting the critical section state, the site is blocked and cannot make further requests for the critical section. In idle state, the site is executing outside the critical section. In a token based algorithm, a site can also be in the state where the site holding the token is executing outside the critical section, and this is called an idle token. So, at any instant, a site may have several pending requests for critical section. A site queues up these requests and serves them one at a time. Requirements of mutual exclusion algorithm. The primary requirement is the safety property. At any instant, only one process can execute the critical section, and this is the most important property, essential property it is. The next requirement of a mutual exclusion algorithm is the liveness property. This says that this property states that absence of deadlock and starvation should be maintained. That means two or more sides should not endlessly wait for the message which will never arrive, and this is an important property. To ensure the mutual exclusion. Third property is called a fairness. So, each process gets a fair chance to execute the critical section. Fairness property generally means the critical section execution requests are executed in the order of their arrival in the system, and this order of arrival is determined by the system of logical clocks, and this is also an important property for the different distributed mutual exclusion algorithms. So, this is the essential. The first one is the essential property, the other properties are important properties. Now, we are going to see the performance metrics, and these performance metrics are used to compare the algorithms, distributed mutual exclusion algorithms. So, the first property is basically performance metric is called message complexity. So, message complexity is the number of messages required per critical section execution by the site. Second is the synchronization delay. So, after a site leaves the critical section, it is the time required and before the next site enters the critical section. So, here we can see that after a site exits the critical section and a new site when it enters, that particular delay is called a synchronization delay. So, when a site exits the critical section, there are certain rounds of message exchanges which will prepare the system so that the next request or next process can be allowed to go into critical section, and that is why synchronization delay in some of the distributed algorithms are basically seen. Third performance metric is called basically the response time. The time interval a request waits for its critical section execution to be over after its request message have been sent out, and that is called response time. So, here when the request message has been sent out till the site exits the critical section, the entire duration of the time is called the response time. The fourth metric is called system throughput. The rate at which the system executes the request per critical section is called system throughput. System throughput can be calculated using a formula, that is 1 by SD means the synchronization delay plus the average execution time, where SD is synchronization delay and E is the average critical section execution time, and that basically will compute the throughput of the critical section execution. So, these are 4 performance matrices we have seen, and we are going to use it to compare different distributed mutual exclusion algorithms. Now, another performance is about high load and low load situation. So, we often study performance of mutual exclusion algorithm under 2 special loading conditions, that is the low load and the high load. The load is determined by the arrival rate of critical section requests. Under the low load condition, there is seldom more than one request for the critical section present in the system simultaneously. Under heavy conditions, there is always a pending request for a critical section at a particular site. So, non-token based approaches. Lamport's algorithm. So, Lamport's algorithm is first in this particular class of non-token based algorithms. So, in Lamport's algorithm of distributed mutual exclusion is using the system of logical clock, which is designed by the Leslie Lamport. So, this particular algorithm is a demonstration of use of the Lamport's clock in designing the distributed mutual exclusion algorithm. So, Lamport's algorithm, requests for critical sections are executed in the increasing order of the timestamp, and the time is determined by the system of logical clock, and this will ensure that this is a fair algorithm. So, that means this algorithm ensures the fairness property. Fairness property, that means the order in which the requests are arriving and they are being served in that particular order, and that is ensured by the use of logical clocks that we will see here in this algorithm. Now, every site Si keeps a queue, that is called a request queue of a process I, which contains the mutual exclusion request ordered by their timestamps. This algorithm requires the communication channels to deliver the message in FIFO order. There are three types of messages used in this algorithm. They are called request message, reply message, and release message. These messages with timestamps also update the logical clock, that we will see in the algorithm. So, the algorithm, Lamport's algorithm for non-token based approach for designing the distributed mutual exclusion. The first action is requesting the critical section. So, when a site Si want to enter the critical section, it broadcasts a request message, and request message has the parameter, the timestamp of and the process ID, that is I. So, the request message contains the timestamp request message of process I, and this message will be broadcast to all the other sites and places the request on its request queue also. Now, when a particular site Sj receives this request message from Si, this Sj places the site Si's request on his request queue, that is request queue of j, and also returns a time stamped reply message back to Si. So, these two actions we have seen, that is to request for the critical section execution by a particular process I. Now, second part of this algorithm is about executing the critical section. The site Si enters the critical section when the following two conditions hold. The first condition says that Si has received a message with a timestamp larger than TSI from all other sites. So, that means Si's or site I's message is basically having the lowest timestamp. So, it is having the highest priority, and that is why it is executing inside critical section. Another condition is L2 condition, says that site Si's request is at the top of the request queue. Also, if you see the request queue, the I's request will be at the head of the queue. These two conditions are ensuring that a particular process I is executing the critical section. Now, third part of the algorithm says that once a particular process finishes the critical section execution, then it has to release the critical section execution. So, releasing the critical section, a site Si upon exiting the critical section removes its request from the top of its request queue and broadcast a timestamp release message to all other sites. So it will send the release message. So and also it will remove I from the queue, and the release message will be broadcasted. So when a site Sj receives a release message from Si, it removes Si's request from its request queue. So when a site removes a request from its request queue, its own request may come at the top of the queue, enabling it to enter into the critical section if it is interested for, or if it is requesting to go in a critical section. Now correctness. So theorem, Lamport's algorithm achieves mutual exclusion. That proof goes like by contradiction. Suppose the two sites Si and Sj, they are executing inside the critical section concurrently at the same instance of a time. So for this to happen, these two conditions must hold L1 and L2 at both the sites. This implies that at some instant in time, let us say t, both Si and Sj have their own requests in the top of the request queue, and the condition L1 holds at them. So without loss of generality, assume that Si's timestamp is smaller than the timestamp of the request j. So from condition L1 and FIFO property of the communication channel, it is clear that at instant t, the request of Si must be present in the request queue of j. So this implies that Sj's request is at the top of its own request queue, when a smaller timestamp request, Si's request, is present in the request queue of j, and this is a contradiction. So hence it is proved that Lamport's algorithm achieves the mutual exclusion. Another theorem is about Lamport's algorithm is about fairness. So Lamport's algorithm is fair. So I have told you in the beginning that this Lamport algorithm is fair algorithm. The proof goes like this. The proof is by contradiction. Suppose a site Si's request has a smaller timestamp than the request of another site Sj, and Sj is able to execute the critical section before Si. So for Sj to execute the critical section, it has to satisfy the conditions L1 and L2. This implies that at some instant in time t, Sj has its own request at the top of its queue, and it has also received the message with a timestamp larger than the timestamp of its request from all other sites. But request queue at a site is ordered by the timestamp, and according to the assumption, Si has the lower timestamp. So Si's request must be placed ahead of Sj's request in the request queue, and this is a contradiction. So this basically proves that the Lamport's algorithm is fair. Lamport's algorithm example. Let us have three sites S1, S2 and S3 participating in the distributed mutual exclusion. Now site S1 and S2 are requesting for the critical section. So S1 will send these arrows, and S2 also will send or broadcast this message to all other sites. Now S1 after receiving so these sites are now S2 after receiving the message from S1 compares with its own timestamp or a request timestamp and particular process. So 1, 2. So basically it is found that the incoming request is having lower timestamp, so it will send a reply back to S1. And similarly S3 is also neither requesting nor it is executing critical section, it will also send the reply. So, S1 will receive the replies from all other sites. So, now S1 will enter into the critical section. Now, when site S1 exits the critical section, then it has to send the release message. So, release message will be sent to all other sites, and after receiving the release message, site S2 will basically will found itself on the top of the queue. Now, after receiving the reply message also from S1, the S2 can go into the critical section. So, if we see the performance of Lamport's algorithm, for each critical section execution, Lamport's algorithm requires n-1 request messages, n-1 reply messages, and n-1 release messages. So, the Lamport's algorithm requires 3 n-1 messages per critical section invocation. The synchronization delay of this algorithm is T, so that you can see that once a particular process S1 exits the critical section, then it requires this message exchange, that is the release message, to flow, and that will take only T time till S2 can go into the critical section again. So, the synchronization delay in this particular algorithm is given by T. Optimization of this algorithm. In Lamport's algorithm, reply messages can be omitted in certain conditions. For example, if site Sj receives a request message from Si, after it has sent its own request message with a timestamp higher than the timestamp of site Si's request, then site Sj need not send the reply message to the site Si. Because Sj's timestamp is lower, so it is having higher priority. So, this is because when Si receives the site Sj's request with a timestamp higher than its own, it can conclude that site Sj does not have any smaller timestamp request which is still pending. With this optimization, Lamport's algorithm requires that between 3 n-1 to 2 n-1 messages per critical section invocation. Now, the next algorithm which we are going to discuss in the non-token based approach is called the Ricart-Agrawala algorithm. The Ricart-Agrawala algorithm assumes the communication channel RFIFO also. In this algorithm, same assumption is there. The algorithm uses only two types of messages, request and reply. So, this particular algorithm is not going to use the release message. The process sends a request message to all other processes to request their permission to enter the critical section. A process sends a reply message to a process to give its permission to that particular process. So, processes used Lamport style logical clocks to assign the timestamp to the critical section request, and timestamps are used to decide the priority of the request. Each process PI maintains a data structure which is called a request default array RDI, the size of which is same as the number of processes or the sites in the system. So, initially the RDIs for all I and j, they are initialized to 0. So, whenever PI defers the request by Pj, it sets RDI of j is equal to 1, and after it has sent a reply back to the Pj, it resets again RDI of j is equal to 0. Let us see the use of this default replies in this Ricart-Agrawala algorithm. Description of the algorithm. So, the first step of the algorithm is requesting the critical section. So, when a site Si want to enter the critical section, it broadcasts timestamp request message to all other sites. Now, when Sj receives a request message from site Si, it sends a reply to the site Si. If the site Sj is neither requesting nor executing critical section, or if the site Sj is requesting and Si's request timestamp is smaller than Sj's own timestamp, then also it will send a reply. Otherwise, the reply is deferred, and Sj will set the RD parameter of I is equal to 1. Now, second step of this algorithm is executing the critical section. Site Si enters the critical section after it has received the reply message. From every site, it sent a request message. When a site Si exits the critical section, it sends all the default reply messages. So, for all j's, if RDI of j is equal to 1, then it sends a reply message to Sj and sets RD parameter to 0. Note that when site receives a message, it updates its clock using the timestamps which are basically piggybacked in the messages. So, when a site takes up a request for a critical section for processing, it updates its local clock and assigns the timestamp to the request. Now, correctness. Ricart-Agrawala algorithm achieves mutual exclusion. So, proof is by contradiction. Suppose two sites Si and Sj are executing into the critical section concurrently. Si's request has higher priority than the request of Sj. Clearly, Si received Sj's request after it has made its own request. Thus, Sj can concurrently execute the critical section with Si only if Si returns a reply to Sj in response to Sj's request before Si exits the critical section. However, this is impossible as per the algorithm is concerned, because Sj's request has the lower priority. So, it will defer it. So, that is why both the assumption that Si and Sj both are executing critical section is contradicted. Therefore, Ricart-Agrawala algorithm achieves mutual exclusion. Ricart-Agrawala algorithm example: assume that site S1 and S2 are requesting for the critical section, and they will send the message to all other processes. Now, you can see that when S1 will receive this particular message from S2, and the timestamp of S2 is basically higher than the timestamp of S1. So, S1 is having higher priority, so it will defer it and put in the data structure RD of I, the value of j will become 1. Now, after receiving the replies from all other sites, these are the reply messages. The site S1 will go into the critical section. When site S1 exits the critical section, then it will send the replies to the deferred messages. So, basically the request which was deferred, it will send the reply to that particular message. Now, S2, which is also interested to go in a critical section, now at this point of time it has received the replies from all other messages and it will enter into the critical section. Performance of this algorithm: for each critical section execution, Ricart-Agrawala algorithm requires only two types of messages, that is request and reply, and n-1 number of request messages, n-1 number of reply messages. So, total number of messages required per critical section execution in Ricart-Agrawala algorithm is 2n-1 messages only. Synchronization delay is the same as you can see in this particular picture, that once site S1 has come out of a critical section, then it will take t time to send the deferred messages. Then only the next process which has requested to go in a critical section can basically enter into critical section. So, the synchronization delay SD is basically T that we have expressed here in this algorithm. So, the conclusion, mutual exclusion is fundamental problem in a distributed computing system, where concurrent accesses to the shared resource or a data is serialized. Mutual exclusion in a distributed system requires not only one process be allowed to execute the critical section at any given time, and also ensures the fairness at the same point of time. So, in this lecture we have discussed about the concepts of distributed mutual exclusion, and we have also seen the non-token based approaches like Lamport algorithm and Ricart-Agrawala algorithm to basically achieve distributed mutual exclusion. So, in the upcoming lecture we will discuss about the other schemes which are quorum based schemes and token based approaches. Thank you.